So we will start with our first presentation, and that will be held by Danny Behnecke. He is working for the German Aerospace Center, DLR, and there he is at the Institute of Transportation Systems. In the set-level project, he's the work package lead for coupling mechanisms of simulation models. And furthermore, he is responsible for development of the set-level modular simulation platform architecture. And today he will speak about automated simulation of scenario sequences. And before you start, Danny, just let me say to our audience, please remember you can use the chat function, make use of it frequently, and let us know all that is on your mind and the questions that you have. Now, Danny, warm welcome to you, and it's your stage.
All right, thanks for the kind introduction, and let me get to it and tell you how we're going to plan to automate the simulation of scenario sequences with the results of this set level project. First, a little recap. We all had a lunch break, so although you've already heard earlier today that highly automated driving is a very, very complex thing to develop and even more complex to test, we're also facing a topic that has evolved for decades now and is dealing with a lot of different requirements, domains, goals, and technologies. Mitigating that kind of diversity requires some kind of automation to translate these domain knowledges to code and keep things manageable. As this automation itself will be complicated in setup, a workbench framework will be needed to represent this automation-based workflow to solve the upcoming problems cleanly and separately. To achieve such an instantiation, let's first have a look at what is meant by automated configuration and why we chose a platform architecture. Automation in general will save time. So far, so old. Automated configuration, however, will be something new. When the information how modules and simulation models have to be connected comes from a single source of truth, a new flexibility in creating tool chains is gained. This flexibility means you can adapt to new circumstances, and the freed up resources and mental capacities can be used to test new approaches and solve the more important problems. And why exactly a platform architecture for this endeavor? Well, platforms are not only one of the best practices for large-scale software systems, but that design fits perfectly with the prior required features we need to maintain automated driving's complexity. When interpreting a platform as an assembly of microservices or microservice-alike components, you can get the sought-after flexibility and gain independence of monolithic hand-integrated solutions of today. It is only feasible if interfaces between those components are standardized. This will give you the freedom to use no experts needed abstraction levels, and it frees you of the responsibility to also having to maintain set systems. Having said that, let's have a look at what we're talking about. On a very high level, simulations involve some kind of descriptions, what to do and how a system that does the simulation should be working together. Then we need some data storage and an evaluation systems that produces the report in the end, which says yay, nay, or gives the user a more elaborate evaluation of the result. These systems are currently connected very differently in different companies, which involves a lot of fiddling and tweaking to make everything work just right in the first place. And then you have to reinvest that work again when you want to have some change some part in that tool chain. Now, let's imagine you wouldn't have to do that. Imagine all valid connections are predefined and you only had to activate them according to your needs. So for argument's sake, let's display them in some kind of bus. To activate these connection automatically, you're in need of some component that will take the responsibility of managing all that. So we've added one and gave it the name of Simulation Platform Management. And to obtain all needed simulation components from a single source, let's also connect up some repositories to said bus. And now just let us think through how these components might play together. First, we've got our task description and configuration artifacts that are read by the simulation platform management. The management will deconstruct this information and will start up the simulation system, the evaluation system, the needed repositories, and also if your workflow might need that, some external data storage. And the data that has been deconstructed will now be sent through the according systems. So something to the simulation system, some others to the evaluation system, and your simulation is being executed. Once that's done, the simulation system then, depending on your workflow, will either put your data into the external data storage or send directly to the evaluation system, where it then can be analyzed and create a report that the user wants to see. That as a rather crude and general setup. So let's just take a deeper dive into the respective roles of these components to put everything to a whole picture together in the end. Let's start at the top. We're having the simulation platform management that not only gets the task description and some kind of information how the simulation platform has to be configured, but also will get the evaluation results itself as a feedback loop from within the platform. Its tasks are to generate concrete scenarios, if necessary, when it's been given logical ones. It has to initialize the simulation platform itself and pass on scenario and other instantiation data. And last but not least, it has to orchestrate all the different tasks according to the description. These task descriptions mainly will be sent to the simulation system, which will not only get the concrete scenario, but also instantiation data and execution instruction. And its job is to instantiate scenarios, simulation models, test objects, and everything that is needed to execute a simulation. Furthermore, it drives the interfaces for set software components and provides also interfaces for probably needed core extension. Then, of course, it has to simulate the traffic events that are specified in our task. And last but not least, it's going to record these simulation results, which then, according to your workflow, will either be sent to the evaluation system if you're aiming at an online evaluation, or to the external data storage if you're aiming at an offline workflow. It doesn't matter where you choose to store it. In the end, these data will be fed to the evaluation system, and there it will be analyzed. Besides the this simulation data, the evaluation system gets also evaluation criteria from the task description and runtime commands according to this description as well. Keep in mind that the simulation data represents traffic situations occurring in this simulation and will be then here evaluated according to these evaluation criteria. These results will be sent back to the platform management, where the decision might be made that some scenarios have to be resimulated, or that you might have to go down another avenue down your scenario exploration algorithm, depending on what this simulation resulted in. And eventually, once these reoccurring loops are finished, you're going to generate the result report in here, here called evaluation report, and send this back to the user. Just on a side note, according to repositories, those can hold all sorts of components, simulation models like vehicle dynamic models, simulation core extensions like observers for not already recorded metrics by the base simulation system, or evaluation models that contain specific methods depending on set extra metrics, for example. Using this approach, you're enabled to have one single source of truth for every component that is not already part of another service, like test object components or complete digital twins. This way, syntax is already defined and leaves no room for confusion. All right, now I've been over all the important components. Now we're going to take a look how we translated this abstract idea of a simulation platform into a conceptual architecture that realizes everything I've been telling you for the past minutes. Spoiler alert, you've already seen this picture, but hopefully now you've got some more context. We're also currently working on a paper regarding this architectural concept, so with a little patience, you'll get it in a citable way. Also keep in mind, those connections you're seeing here merely depict data flows and are not taken for concrete connections. This is on a conceptual level. Speaking of concepts, when you have a concept, you also have to prove that it's working. That's why I also want to represent to you the idea of the research implementation. I started this talk with a claim that complex problems need a clean and precise workbench to test out things, and ideally this testing is being conducted within the solution space of industrially used tool chains. And that's why we're planning to set up a research implementation that will be built out of open software components, so every interested party has the opportunity to experiment with it and get a little head start when it comes to entering this field of research. Feature-wise, it will demonstrate the setup and execution of simulations from one configuration source, as well as the viability of our architecture. The workflow with the research implementation will be as following. You'll have a GUI where you can create your simulations to be executed, including specifying parameters, maps, scenarios, and the test object, which for now will be consisting out of the simulation models provided by the set level project. With one click, you're going to send your information to the platform, which will do your simulations, and once it's done, sends back an analysis report of the chosen traffic situations. And now, before you get lost in this rather similar looking diagram, just let me explain. As I said, the platform itself has a simulation system at its heart. Since our goal was to provide the platform consisting of open source software only, we have chosen the Scala simulator for our first approach for a proof of concept, so that we can show everything is working together. For all of you who have never heard of Scala before, not a problem. Basically, it's an open project that utilizes the Unreal 4 game engine to provide simulation features. Their website is carla.org if you want to have a look, but for set level, they will just be the first simulation system we are going to plan to make integratable with the platform demonstrator. For those of you who have already heard of Carla, you might be asking yourself, well, it's already a complete simulator. What did you do then? Well, when you're trying to create an assembly out of systems who aren't from the beginning designed to be assembled, you leave yourself much room for surprises, if you will. So this was the same here. We are going to concentrate on bringing FMI and OSI to Carla and plan to publish this feature within this project year as a merge request. Currently, we're in the middle of the last integration tests, and if everything goes according to plan, within the next month, you can find everything we did on GitHub. And after this is done, our next goal is to bring the automation into the automated configuration of the platform. All right. As key takeaways, this was probably a lot to take in, so we've prepared some key takeaways for you. The points aren't going away in your short-term memory. Our approach is based upon a single source of truth for all your configuration needs and automating the setup completely according to that information. I've presented to you the concept of an architecture, how a simulation platform for scenario-based testing can look like. And also I've teased you a bit about what we're going to publish as a proof of concept so you can get started experimenting yourself. That's so far everything from me. Thank you for your attention. And do you have any questions?
Yeah, thank you, Danny. Thank you very much for your presentation. Yeah, we have Jochen with us to address the questions from our audience to you. Jochen, are there any questions?
Yeah, of course, there are some of them. I would just like to start with one question. You mentioned Carla as a core simulation platform. So maybe you can elaborate why you have chosen Carla, and do you have any experience yet in using it? So maybe you can talk about this a little bit.
Yeah, certainly. So as already mentioned, that open source is a big thing for us in this platform. Carla was a fitting opportunity when we started planning everything, and as we are primarily focused on SUC2, it seemed very fitting for us to use Carla as a currently, let's say, on vogue simulation, open simulation tool. And our experience is basically what I tried to hint at earlier. Carla isn't really meant to be part of a bigger assembly of systems, which also is seeable in how their interfaces are currently designed. And we started to get in touch with the maintainers to change that.
Okay, thank you. So maybe another question that is similar to that. Do you have any other middleware that you use to implement this modular simulation platform, or is it Carla itself?
No, it's not Carla itself. Carla is just one component of this. Currently, as middleware, we're trying to be as let's say neutral in terms of using a specific middleware as possible. So for our first demonstration, the connections between the components are realized purely over either FMI OSI when talking about the simulation system itself, or over Google RPC or gRPC protocols, as this was or is rather compatible to the current technology of OSI.
Okay, thank you. So you talked already about these interfaces and the standards. Maybe if we go to what you call the bus, do you have already introduced some standards how these microservices are communicating and how the data is transferred?
Currently, not yet, because we're still having had a lot surprises which came at the Kala front. But we're looking forward to to implement these connections, hopefully through standards like the XIL API in the second project half.
Okay, so there was another question regarding the co-simulation. So have you already used any co-simulation tool to combine the simulation and all the artifacts, including the device under test?
Not yet. Currently, we're still in hand integration mode, and we're for now trying to keep it that way or keep it like that as we try, at least for a first demonstration, to introduce as few tools as possible, so we have a minimal viable setup which can be expanded upon in the near future.
Okay, I think there is also already some interest in doing own experiments with your platform. So the next question would be: is there any licensing or also is it really for free for people in industry and research to use that?
Well, the FMI and OSI implementations we plan to put under the same license as Kala, which should be MIT, if I'm not mistaken, as those, or as we hope that those features will be part of the Kala ecosystems itself. Regarding the platform management and evaluation system and everything that will be added upon, there will be some open source licenses. Which license directly, I currently can't really say, but accessibility is one of the big selling points here. So I'm cautiously hopeful that this will be the case.
Okay, thank you. So maybe another question. As your platform is quite modular, and you also talked about the microservices and so on. So do you think, or do you plan to make your platform also executable on the cloud?
Well, see, in general, we plan to encapsulate all of the components inside of containers of some sort, either Docker or whatever we are then able to use at our own infrastructure. So I don't think that there should be big hurdles of migrating to a classical cloud infrastructure from our test environment. Or at least everybody who wants to use it should be enabled to do that with this solution we're aiming at.
Okay, thank you. So I think we have still some time for questions.
Ooh.
2 questions.
Yeah, fine. That's fine.
Yeah, so maybe as there is no additional question from the audience, maybe one final question from my side. So we had already a lot about standards like Open Scenario, Open Drive, OSI, FMI, SSP, and so on. And all of these standards are not ready yet, so they are under construction and not completely mature. So how do you handle the changes of these standards? Or have you some plans how you want to handle the evolvement of these standards?
Yes, actually, I think the open source approach, at least for this demonstrating project, will help us in that, as we when we want to go open source, you're basically forced to do it cleanly. Otherwise, you can't succeed when there are other great projects out there that handle it better than you. And I think this, this forced cleanliness in your code also supports a good maintainability. And that at least is my guess that how we could handle all the changes that we will be seeing in the future.
Okay, so there is now last question. Where can we find the contact details of Danny?
Yeah, good question. I think that's one thing I forgot on my slides. I guess we can probably put it on the website. I don't know. Otherwise, just denny.behnecke@dlr.de.
Okay.
Okay, so thank you very much. There were some other questions in last second, but I think we have to skip them now. So
Yes, that's fine. I think Danny answered a lot of questions. Thank you again, Danny, very much for your presentation.